Good afternoon, everyone. I don't know if you can hear me well. If anyone doesn't hear me, just raise the hand, or you can write on the chat view also. So, good afternoon. My name is Theodore Tsirozidis, and I'm the Sales and Marketing Manager of Tech Science, which is responsible for the distribution of IDEA StatiCa solution in the UK market. I would like to welcome everybody in our webinar today, which is dedicated to steel connection design. Together with my colleague, Kostis Hatzopoulos, the Technical Support Manager of Tech Science, we're going to present you IDEA Connection, a revolutionary software that is based on a new method called CBFEM. It's an acronym for Component-Based Finite Element Model. And the reason we organized this webinar is that since January that we officially launched IDEA Connection in the UK market, we had a very big number of requests from companies all over the UK and also other parts of the world like Australia and Canada that wanted to see the software, and since it is difficult to do that personally, a webinar can help to get a basic knowledge of IDEA Connection, what it is about, and what it can do. So without any further delay, I will start my part of the presentation, which is an introduction to the basic concepts of the software. And then I will switch the screen to Kostis, who is going to show you a real example, a real connection from the initial modeling to the analysis and design. So before we start anything, I just wanted to mention that you have, for anyone that is not familiar with the GoToWebinar software, in the right part you have a control panel and you can enter any question that you have. So at any point, please, if you have any question, just write it on the chat. And we will answer these questions after the presentation. Also, if you want to hide the control panel, there is an orange arrow so that it doesn't block your view. So, during the last couple of decades, there has been a lot of development in the area of finite element analysis that, of course, has helped enormously the work of a structural engineer. And there are many tools that provide a very accurate analysis of steel structures in a 3D environment without any limitation to the number and shape of members, and also a lot of designing capabilities according to the codes. So in a few words, in that area, engineers are fully covered and have a lot of different alternatives. But despite the fact that most of the failures in steel structures come from bad design of connections, the development of sophisticated code checking tools based on FEM has been very poor, and the majority of available software has a lot of limitations in the topology of the connection and the design itself. The main reason for this limitation and the lack of flexibility is the fact that they are all based on the component method, which I'm sure that you already know. Component method can give reliable and accurate results for simple topologies, but it is simply not enough for more complex ones. So until now, we were able to design simple connections like this, as you see in the screen. But what about this? Or this? Or even this? So all these connections were very difficult to design, and usually they are designed by hand. To answer to all this, the answer to all these difficult connections is CBFEM method, and this is as we like to say, is the future of steel connection structural design. CBFEM is a new way to analyze and design connections, that we believe it is really a big step forward in structural engineering, and will be the future, possibly not only for connections but for steel in general. First of all, it would be useful to have some background on existing component methods for anyone that is not really familiar with it. Component method is based on the fact that it starts, let's say, with a decomposition of a joint into different components, followed by their description in terms of normal, shear force, deformation behavior. After that, the components are grouped to examine joint moment rotational behavior and representation in a spring shear model and application in global analysis. The advantage of the component model is the integration of current experimental and analytical knowledge of connections, components behavior, like bolts, welds, and plates. This provides very accurate prediction of the behavior in elastic and ultimate level of loading. And the verification of these models is possible using forces distribution, but it can be done by for a limited number of joint configurations. In contemporary scientific papers, the description of non-typical components is either not present or has low validity and description of background materials. For example, models of hollow section connections are described in Chapter 7 of Eurocode, Eurocode 8.8, by curve fitting procedures, but their compatibility with component model is unreliable. So CBFEM, as we say, is the evolution of steel design, and it is actually a synergy between the traditional component method and finite element analysis. In a few words, CBFEM allows us to analyze and check according to the codes any connection, no matter how complex it is. So a main point that you have to know is that we are not replacing the component method, we are just taking a step further. So as you can see here in this slide, CBFEM is based on the decomposition of the whole joint into separate components, steel plates, welds, bolts, anchors, or concrete blocks. And each component has its own analysis model. So 2D plates, for example, finite element, 2D plate and walls are finite elements for we use a shell model for that. Force interpolation constraints are used for the welds. Nonlinear springs are used for bolts and anchors. And contact elements between plates in connection. So we have special contact elements that are positioned between a base plate, for example, and the concrete block. Of course, if we want to calculate connections properly, we need to use plastic nonlinear analysis. And in our solution, we use this ideal plastic material model with elastic part and plastic part. And as we cannot check stress because of yield stress limit, the check of plates is done for limit of equivalent plastic strain, which is recommended to be 5% according to Eurocode 3. Of course, there has been a lot of verifications for the CBFEM, and as you can see here in this diagram, you see that we have a simple connection, moment, welded frame moment connection, and we can see that it gives almost the same results as the component method. Of course, we have several verification examples, and in the end of June, a book also will be released by Professor Welds, who is actually one of the people that is behind the creation of this new CBFEM method. Professor Welds, of course, is one of the most known people in the industry. He's currently working on Eurocode. He's in the Eurocode committee for the connections. And he will publish a book that will contain a lot of benchmark cases for steel connections, and that will be very useful for anyone that wishes to see to verify the how CBFEM is calculating connections. At the moment, IDEA Connection is the only software in the world that implements CBFEM, and this is what we're going to show you later on. So what are the main features of IDEA Connection? First of all, we have introduced a new solver. And you probably know that when you are working in general finite element software and you want to connect two plates, you have to solve the intersection between these two elements. And the mesh in that area is usually deformed and with higher density because of the intersection. If more plates, of course, intersect close to one point, then the situation gets even worse. So we follow a completely different approach for the mesh. In our solver, the plates do not intersect, but each one is independent, and all the internal forces pass through connecting elements, like welds and bolts. These connecting elements are modeled using special force interpolation constraints. So you can imagine it like a short lever arm between the nodes of connected plates. This way we can connect members properly, so we do not increase the number of mesh elements, and we keep the mesh as simple as possible. And of course the advantage is that we have exact forces in all the welds and the bolts. So we are able to check afterwards individually all the bolts and the welds. So at this point I would like to give you a short demonstration about this feature. So as you can see in IDEA Connection right now, we have a simple connection. I can also maybe switch to this one, which is, it's better to show this feature. So if we run this calculation, and we go to check, we can enable the mesh. So we can visualize how the mesh has been created. So as you can see, every plate has its own mesh depending on the size, depending on the geometry in general, and the forces that have been applied. And now we have a much better, a more optimized mesh. So you can see that this stiffener, this triangle stiffener, has a much more dense mesh compared, for example, to the plate below or to this member. So each member, each element has its own mesh, and everything is connected through the welds. So at this intersection, as you can see here, so there is no real intersection between the elements, but between them there is a weld that actually take all the forces from one element to the other. So I will switch back to my presentation. Also, we have introduced a new way of modeling, which is very simple and easy to use. And of course, we cover everything. We cover in terms of topology, so we can model any connection that we want. And the reason that we did this is that we didn't want to have another CAD-like software. So we wanted to have something simple that generates a finite element mesh automatically, so engineers do not get dragged into complex modeling. So let me give you a small also demonstration of this modeler. So I will go back to this connection. So as you can see, we have defined some basic elements, and if we want to add another member, we don't have to actually draw it as CAD software usually do, but we go to the geometry, and as you can see here, we have 3 members, and we can, for example, add another member. And of course, we can change the pitch. So everything is done through a drop-down menu. So we just enter a new member, and then you have all these different properties that help you to model exactly the member that you want. So if, for example, I need a rotation or a direction, maybe 15 degrees, or a rotation, you see that now it is rotated compared to the other components. So everything is done very easily through different options here in this menu. So the engineer doesn't have to actually draw anything, he just chooses through the different options. So also we have introduced a new, another, let's say, feature called manufacturing operation. So the basic idea was, as I told you, was not to create a CAD program, but a program for engineers. And an engineer should communicate with the program in his language. That means that in that sense, we organize IDEA Connection workflow with the same way as the real manufacturing workflow. So this means that if you're creating a connection by putting together different plates, haunches, ribs, widener, and then you have to cut them, you have to weld them, you have to bolt them together, exactly as is done in a manufacturing workflow. So let me give you just a small overview of this. So going back to the previous connection, as you can see here, we have some stiffeners in the member. So let's say, for example, that I want to drill a hole in this stiffener. So the only thing I have to do is to go to design. I will find the stiffener, which is this one, and then I have an editor which helps me to make any modification that I want in this plate. So for example, in this case, I need a hole. I just enter the hole, and I just define the size, the diameter. Let's say, for example, it's 50, and I can position this in a different point. Let's say -20 and -20. So if I click OK, I can see that I have just entered a hole in this stiffener. So this is the different approach that we follow that we call manufacturing operations. And manufacturing operations can be any of these, as you can see here. So all possible things that are happening during a manufacturing operation is there. So you can cut, you can weld, you can bolt some elements together, you can create connecting plates, so anything is possible through this menu. Bolts intention. Bolts, the analysis model regarding molds needs to take some important things into account. Firstly, we need to analyze the contact between the two plates. Plates in contact can work only in pressure. So you can see here in the slide that there is an opening between the plates. an open contact. Frequently bolts only work in tension, so we need to use a proper diagram which takes into account plastification and other effects when bolt is close to limit force. Bolts in shear also are modeled as nonlinear springs. They are in contact with the steel plates holes only in the zone of pressure, as you can see in the picture. And the distribution of shear force from bolt to hole surface is realized by a special contact element and interpolation constraints. And these things, this solution is protected by a patent for our company. The welds is the same. So welds are modeled as interpolation constraints, interpolation force constraints. There is no intersection between the plates, so all stress goes through the constraints. And you can see here the different possibilities that we have concerning the weld. So it can be a fillet, a double fillet, a butt weld, or we can have no weld at all. The concrete also is modeled as Wingler-Pasternak subsoil, so it's not modeled by finite elements. But we use this model as similarly to designing buildings. In each point of the mesh of the base plate, we have contact elements and spring, which represent the stiffness of concrete block. We also take into account the mortar joint. Anchoring bolts are modeled also as non-linear springs, and of course all appropriate checks according to the codes are implemented. In this model we calculate contact stress under the base plate, then we derive the effective area like in Eurocode and calculate the average stress for this effective area, which is checked for concrete ultimate capacity. Design resistance can be defined, can be calculated by two ways. We can apply all loads and calculate until the end the connection. So you can see that in the left part, you can see that this connection is loaded too much, so it fails. Or we can set IDEA connection to stop the analysis when the limit of strain is reached. So we apply the load and we calculate until we get this 5% limit, and then we stop. IDEA connection tells you how much load you actually applied, and in this case, as you can see here, it's 93.4, and you actually get the design resistance of the joint. We are also able to calculate the rotational stiffness of the joint, so we can also calculate automatically the class. So you can see here that this is classified as a semi-rigid connection. So there are three stages. It can be either thin, semi-rigid, or rigid. And this is calculated automatically by the software. We are also able to make a buckling analysis, which is quite unique in our software. And this gives you a very good idea about buckling, which is a very important issue when it comes to steel design. And of course, in IDEA connection, we assume that the connecting members cannot buckle, so they are designed properly in the global, let's say, analysis software that you are using. And we only deal with a local buckling that is happening inside the joint. In this example, you can see how a stiffening of a joint can be achieved and can give us how buckling analysis can give us an optimized solution. So that means, for example, if we analyze in the left part, it gives us a buckling on the web of the column and gives us a factor of 2.66. That means we have to apply 2 times 2.66 times the load in order for the connection to fail. By introducing a stiffener on the column, we see that the buckling moves to the web of the beam, and that gives us a slightly higher factor. And at the third example, we introduce a stiffener on the beam as well, so now the backlink appears on the widener. And now, of course, the factor is much higher. We also link to other software, which is really important if you want to save time. So we are able to import the geometry and the loads from structural analysis software like CA Engineer, Robot, SAP 2000, Midas, or AXIS-VM. And we can also import the geometry from Tekla structures and advanced steel from Autodesk. So conclusions. First of all, we have an all-in-one solution. That means that with one software, you can make a stress analysis, piping analysis, stiffness analysis, and an overall check. We have total freedom in the topology. That means we can have multiple members from all directions, eccentricities, general cross-sections, general plates, opening cuts, whatever you have, you can just put it in your connection without any limit. Of course, it's a big time saver. That means that you can very easily design a connection, model and design a connection. It can provide a more economical design because of the precise analysis of the model that allows you to simulate exactly the connection, how it is in reality. So in this example, as you can see here, the bolts in the middle do not contribute anything to this connection, so you can take them off without without changing anything in the behavior of the connection. And of course, be on the safe side. That means that you can get complete Eurocode and American codes, and you get a clear, comprehensive checks for all the elements, plates, bolts, and welds. And of course, you get just a simple pass and fail status for all the elements. Every single weld, every single bolt is checked. These are some of our clients in the UK, and thank you for your attention, of course. So I'm going to switch to Kostis so that he can give you an overview of a real example and how we analyze a connection.
Okay, hello. My name is Kostis Hatzopoulos. I'm the Technical Support Manager of Tech Science, and I will be creating from scratch the connection that I'm currently showing you on my screen. So, first of all, does anyone has problems with the sound?
Oh, Kostis, I think we can hear you very well.
Okay, okay. Then we can proceed. So, although this connection is simple, its topology is in the three-dimensional space. This means that this 3D topology creates a complex 3D stress state, which while in our software it's easy to check, it means that in other software you would have to check each member separately or to check each plane separately, and that is the XZ plane or the YZ plane, the connections along these planes. Okay, so let's start and model this thing from start. So we'll create a new connection, and in order to save some time, I will use some of the modeling templates that are already offered by IDEA. So I will go to 3D templates, and I will pick this one, which is close to my connection. So, IDEA created this connection. First I will start from the chord, and there I will change my cross section to an HEA200. Okay, connection is changed, the cross section is changed. Now I will go to the lateral member named V. I will also change its cross section, let's say an HEA140, and then I will proceed with my diagonals. I will switch my view to the XZ view in order to have a better understanding of the manipulations, and then I will go to my diagonal. I will insert a tube cross section. So I'm choosing a CHS, let's say 60.3 by 4. My cross section is changed, and I will also go to the D2 diagonal and change it to a tube. Now the only thing I have to do is rotate them. And I will also add a small offset to these members. Okay, a small offset, -20, so that we need a plate here in order to weld them properly. So, the basic geometry is already there. Now, the only thing we have to do is to start adding our other components, like plates and stuff. In order to do this, I just have to go to the design tree item, and here I will start to apply my manufacturing operations like Theodore said before. First, I will add a plate in order to weld my diagonals. So I'm using the plate manufacturing operation. I will switch my view to the transparent rendering so that I have a better understanding of the positioning of members. I'm assigning this plate to a member, and this member is the chord, and I'm attaching it to the rear of the bottom flange. Again, I'm switching the view, and here I can fine-tune the dimensions. So I'm adding an 80 mm height, and also I'm adjusting the width. So here it is. The next thing is that I want to define how this member is welded. I will use a double fillet weld, and I will leave the throat thickness to 0. 0 means for IDEA connection that the software will calculate the required throat thickness in order for the weld to pass all the checks. Now that we have a plate, I will use this plate to cut these diagonals like we would if we were in the factory. So I'm adding a cut. I will cut the diagonal named D2, and I'm cutting it by using the plate named P1. Again, I can define the welds. I'm leaving the weld value throat thickness to 0. Now that the plate is cutting my diagonal named D2, I also need to apply a similar operation to the diagonal named D1. Since I have this defined for D2, I only copy this operation and change the diagonal. And this is it. Now I have to cut my diagonals by using the chord. So I'm cutting diagonal D2 by using the chord. And again, since this operation is applicable to diagonal named D1, I'm just copying it and changing the name of the diagonal. And this is it. We have created a complex welding geometry quickly. Now, as Theo told before, we have a very rich toolbox of manufacturing operations. So in these operations, there are some common connections. For example, I can connect my member named V by using a shifted end plate. So I'm choosing the bolt size and bolt material, and I can connect my V member to the chord. I can add a stiffener, and I have quickly created a connection. But since we want to show the potential of the software, I will not be using this connection because it's too simple. So I will create it from scratch. Okay, so I will use a stiffener. I'm putting the stiffener on the chord member, let's say of a thickness of 10 millimeter, and I want it to be located in the front only, so that I can connect my V member with a fin plate. I can change my view again so that I can see the dimensions of this stiffener clearly. So I define a round dimension for the stiffener. And now I will connect my V member with a click operation. So my member named V will be connected to an existing plate which is named Stiff1. It is the stiffener I have previously defined. Okay. Next, we change the view in order to fine-tune the dimensions. I'm adding the width of the tank to 100 millimeters and its height to 140 millimeters. I'm also having a 10 millimeter offset for the weldings, and I will also bring it closer to my main member. Now I have to properly position my bolts. So I'm positioning them in relation to my local X axis, and I will bring the bolts a little closer to my member. And this is it. We created a connection which is not so regular. So the next thing is that we must apply some loading in our connection. For this, I'm going to the load effects tree item. There we can see that first we can have many load cases in one project. In our case, I will just use one load case, and as can be seen in the table, each member can have up to 6 stress components. Sometimes this is especially when the model comes from the BIM workflow. This is very useful, but in our particular case, especially for the diagonals, the definition of all these 6 stress components gets in the way. So I'm going back to the geometry and I'm defining them to receive only axial load. So if I go back to the load effects, the relevant stress components are deactivated. And let's define some tensile force of 20 kilonewton on each of the diagonals. And then I will apply a shear force in the lateral member of, let's say, minus 50 kilonewton. Our connection is ready for analysis. So let's go to the check tree item and press the calculate button. The software is calculating. It performs the nonlinear plastic analysis that Theo described. So the calculation is over, and the software is showing a summary table. The summary table is showing that the plates are okay, all our welds are okay, and if you remember, we defined our welds to be 0. That is, that the software will calculate the required throat thickness in order to pass the checks. So all welds are passing the checks, which comes naturally. But we have a problem with bolts. So let's elaborate on this. In order to do this, we have to go to the relevant tab here. If I press the bolts tab, I'm seeing the bolts and the plate which they are bolting. I can see that the developed forces. So, since the resistance per shear plane is this value here, there are 2 alternate ways that we can try in order to make this connection pass. The first is to change the material of the bolts, and the other is to increase the shear planes. How can we do this? It's very easy. I can go back to my design in my clip. First I will try to change my bolt, the material of my bolts. So I pick the 8.8 material. I calculate again. And I can see in my summary table that the bolts are passing the check. Alternatively, I can revert back to my initial bolt material grade, and I can add very easily a second shear plane by adding an additional cap plate, as you can see here. So I also try this alternate configuration, which is also passing the checks. So this is a typical workflow of IDEA Connection, and you can see how easily we can play around and modify things. So let's go back to the check in order to elaborate on the tables a little bit. So this is, now that we have 2 shear planes in our bolts, we can see that the results are provided for 2 shear planes. We have 2 values here, 1 value per shear plane, and of course you can see the utilizations here. Of course we have the Welds table. In this table we see the calculated value for each weld. In the 2D view above, when we select one weld, we see the plate where this weld is positioned. The weld is highlighted with an orange color, and it is also highlighted on the 3D model so that we know the exact positioning. And of course, we can seek for, okay, this is what I was searching for. As you can see, for the tube, we can have the exact welding geometry, and of course the table provides all the required components for the calculation. Just let me show you this drawing, which shows the components just like they are required by the Eurocode. So all these components are calculated for each weld, and they come from these intensities along the edge of the weld. Last, each plate of the connection is presented in this table. There is a 2D view which shows the geometry of the table, and in the table we can also see the von Mises stress and the developed strain. Also, from the results we can have a graph of the stress, an exact graph, a graph of the plastic strain, which is quite low in our case. But what is more important, and it is the criterion for passing or failing, is the strain check, which is quite low for every plate of our connection. Last but not least, there is the report, where we can present the outcome of our calculation. So IDEA presents a nice report. And of course, there are a lot of things that you can add or leave out of the report. What's interesting is the bill of material table, which I will activate and refresh my document. In this bill of material table, you can have each plate and the welds on the table, or the board, the welds on this plate, and the bolts that are bolted on it, and also some drawings that you can pass on your detailer so that he can draw the connection. And one last feature is the ability of the software to have random screenshots. So let's say that I want to add this screenshot to my software. I can have a new picture, and if I go back to my report, I'm just checking the pictures from gallery, and there it is. Of course, I can also have screenshots of stress and strain distributions in my report. Last, I can have the theoretical background, which is useful for the person that is checking our report. So this concludes my presentation.
Okay, thank you, Kostis.